Absolutely. Here you go ahead. Well, Prince puts that up.
That gives me negative 2 over 2. Negative 2 over 2. And
4 minus t to the 1 half.
4 minus t to the 1 half. And then you bring down the other half of the particle, which is 4 minus t to the 1 half. And then you go down and simplify it by finding the common denominator.
That's what's called common denominator. So you're getting a common denominator between these two parts, a fraction and your kind of whole number piece.
Yeah.
So what's your common denominator?
4 minus t.
Yeah, so that denominator. So you multiply that over here, the whole thing. And then you combine them, and what do you get?
Negative t plus 8 minus 2 times 4 minus t to the 1 half. And then you combine like in the numerator, and that's t prime of x. And then now for the proof point, we set the derivative to 0. And that's just.
All right, so the critical value is any value that makes the derivative 0 or undefined. So you get your derivative, your product chain rule, and then once you have your derivative, set it equal to 0 and solve, and that gives you a critical value or a critical number. What would be another critical number for when the derivative is undefined? Is there a value that makes this derivative be undefined? 4. Why does 4 make this be undefined? Because it causes something divided by 0. Now, is 4 something that we care about based on the interval? No. So then we look over here and say, that's not less than 3, so who cares? So this is the only critical number that actually is going to be important for us. But you could get a critical number if they didn't have this stipulation for t of t equals 4 is another critical number. Questions? Was the issue mainly with getting the derivative in the first place, or with once you had the derivative, say here, combining it into a single fraction so that we could then work with it, or did some of you get to here and then try to set that equal to 0 and run into issues? All of the above? Okay. So this kind of situation is why we might want to go through these extra steps with the derivative of getting the derivative to be just a single fraction by combining them together into a single bit with the common denominator. Because once you got it in this form, it's a lot easier to set that equal to 0 and solve it, because you multiply the denominator over, 0 kills it, and you're just left with negative 3t plus 8 equals 0, which is not that bad to work with. But if you have this thing equal to 0, that's kind of obnoxious to try to solve the way that's presented there. Thank you. Any follow-up comments or questions with 13? All right, so from 13, big picture takeaway is, what's a critical number? The critical number is any value for x that makes your derivative equal to 0 or undefined. So you got to be able to find the derivative and then set it equal to 0 and solve for x and find out what x's make it undefined. Then, using that allows us to kind of figure out where we have absolute maximums and minimums on an interval for a function. So an absolute maximum or minimum always occurs at the endpoints of the interval or at critical numbers. So for something like 23, when we want to say, hey, what's the absolute maximum, what's the absolute minimum for this function on this particular interval, what you need to do is find the critical numbers and then plug the critical numbers and the end values into the function and see who's got the biggest y and who's got the smallest y. So for 23, first step is get the derivative so that we can then find the critical numbers. So what's our derivative going to be? 2 and then 2x to the negative 1/3, so this is power rule, minus what? 2. And then once we've got that, it might be helpful to rewrite this as 2 over x to the 1/3 minus 2, so that we don't have that negative exponent running around. Once we've got our derivative, what do we do with it? Equal it to 0. So critical numbers are when the derivative equals 0 or when the derivative is undefined. So set the derivative equal to 0, 2 over cube root of x minus 2 equals 0. How do we solve that? Yeah. Add the 2, then what? Yeah, multiply the denominator over. You have 2 equals 2x to the 1/3. Then what? Divide by 2, and you get 1 equals x to the 1/3. And then how would you kill an exponent of 1/3? Cube it. You would do an exponent of 3. So you cube both sides. And so don't cube root. The 1/3 exponent is a cube root. You want to kill the cube root, so you're doing the exponent of 3. And what's 1 cubed? So x equals 1, that's a critical number. And it turns out that's also one of your endpoints. So that kind of makes life a little bit easier, because that's one less thing that you have to check. Now also we want to see what value of x makes a derivative undefined. How do you know? Yeah, you just see what causes division by 0 somewhere. So you should be able to look at that as, oh, if I have 0 for x and I have 2 divided by 0, that's undefined. So x equals 0 makes this undefined. So those are your critical numbers for this function. Any questions with getting the derivative or then finding the critical numbers? Once you have those, plug them and the endpoints of the interval into the original function to see who's the absolute max and where's the absolute minimum. So over here, we're now checking f of x. So we say, all right, what's y equals f of -1, and what's y equal, because that's an endpoint, y equals f of 0, because that's a critical number, and y equals f of positive 1, because that's both a critical number and an endpoint, and then that's all you got to check, and you see who's biggest and who's smallest. So when you plug in -1, go ahead and do that. What's -1 to the what's -1 to the 2/3? It's just 1. Why is it just 1?
Because you use power over the root. Like the -1 inside the root. You're like,
Yeah.
X -1.
Yeah. So you're squaring it. That makes it positive, and then you cube root it. It's still positive. So that's going to be what? 3 plus 2 is 5. If you plug in 0, what do we get? If you plug in 1, what do we get? So who's the absolute maximum? So f of -1 is the absolute maximum. So here's your absolute max, because that's your biggest y value. Absolute max is 5. So the y coordinate is the max or the min. And the x coordinate kind of tells you where it happens. So the absolute max happens at x equals -1, and there is a max of 5. And the minimum is the smallest y, and that's 0 in this case. So you'd say, all right, your absolute minimum equals 0. And that happens at x equals 0. So once you have your derivative, set it equal to 0 and find when it's undefined and solve for those x's, and that gives you the critical numbers. And then once you have your critical numbers, plug them and the endpoints of the interval back into the function and see who gives you the biggest y, who gives you the smallest y. That gives you the absolute max and the absolute min. And that's pretty much what we want you to be able to take away from chapter 3.1. Any comments, follow up with that? Homework? Cool. Dice? All right, 1, 6, and what's the other one? There we go. Oh, there's 3. 1, 3. Those of you who were absent on Friday, did seeing these and saying that's what's going on with critical numbers and finding absolute max and min, does that kind of clear things? No? Still doesn't? What's the issue that you still have? That's really vague. I can't help you if you say everything. Be specific. Be specific. If you have a problem, I want to be able to fix it. But you got to help me out and be specific in terms of what is the question. Olivia. That would be a good idea. This is on the final. Not that you're taking it. One. So, what in particular? Don't just say everything. Like, what is everything? Is everything like I've suddenly forgotten how to find a derivative because now we're done chapter 2, so I refuse to remember that? Is everything I don't know how to find a critical number because I can't take an equation and set it equal to 0 and solve? Is everything I don't know how to plug a critical number at an endpoint into a function and see who's the biggest y? I don't know what everything is. So you got to tell me what is the issue, if there is an issue. And I know you're not the only one who is. I thank you for speaking up and saying something. So people who are absent on Friday, please raise your hands. All right, Naroz, Kayla, Olivia, anybody else? There were some more people. Muhammad, 2, I think, was out on Friday, but you're still out. Raisa also. So, what do you have like an actual question? Don't just say everything is a problem. I don't know what that means. So, is there an actual question that I can like address? No? Then how do I help you? All right. I guess another review of what we did on Friday. Grace, where did you put those? Could you give those to Rachel, please? And Grace, homework? No? Okay. All right, so major takeaways from chapter 3.1. First, a critical number is an x value for which f prime of x equals 0 or undefined. Cool? Second, a function must have an absolute max and an absolute min on a closed interval if the function is continuous. And third, all absolute maxes or mins occur at edges of closed interval or at critical numbers. And to kind of give you a picture of an absolute max and min, say you have a function on some closed interval from, say, a to b. It's got to be closed, so you have to add actual points at the beginning and the end of the function. And then the function has to be continuous, and as long as those two things happen, you'll have an absolute maximum and an absolute minimum. Absolute just means the very highest or lowest point. So where is the absolute minimum point on this curve? Is it all the way on the right, all the way on the left, all the way on the right, or somewhere in the middle? All the way on the left, because that is the lowest point on the curve. So that right there is your absolute minimum. And then the absolute maximum is where? All the way on the left, all the way on the right, or somewhere in the middle. In the middle, because that's the absolute highest point. That's this guy right here. So that's your absolute max. So there's an endpoint where one of your absolute extrema happen. And then there's a point that's a critical value where the derivative is 0 because of the sharp turn. So for this kind of function, you would want to, whatever the equation is, take the derivative of the equation, figure out where does the derivative equal 0. It's going to be like right here and right here and right here. And where does the derivative be undefined? Right there. And then plug all of those x values and the endpoints into the function and see what gives you the biggest and smallest y value. And since this x value gives us the smallest y, that's your absolute minimum. And since this x value gives you the biggest y, that's your absolute maximum. And these other points would be called relative maximum or minimum points, but they're not absolute. And right now, we're really only focused on absolute maximum and minimum. Yes?
Are the points also relative maximums or minimum?
Nope. So an endpoint can't be a relative maximum minimum, because relative means you're higher or lower than the points surrounding you, and that kind of implies a before and after. And the endpoint doesn't have a before or an after on the other end. So relative maximums and minimums only happen at critical values. They don't happen at endpoints. It's a good question. So those are kind of our major takeaways from chapter 3.1. And kind of, if you read the notes, there's the extreme value theorem that says the function must be continuous on a closed interval. So if you had something like this, does that have an absolute max or minimum? No, because where you should have an absolute minimum, there isn't a point because it's open, and same thing over here. So this is not a closed interval, and so you're not guaranteed to have an absolute maximum or minimum. Now you might, if we draw the curve a little bit differently. Now it has an absolute maximum, but it still has no absolute minimum the way I drew it. So the point of the theorem is like it provides guarantees as long as the conditions are met. The other sort of thing that could break the extreme value theorem in your notes is if you had a break in the curve. Like that. So now you are not continuous, and so that also kind of then violates the extreme value theorem. So in order for us to guarantee an absolute maximum and an absolute minimum, the function has to be continuous and it has to be on a closed interval. So that's kind of like chapter 3.1 in 5 minutes. Any questions? Still confusion? A lot of it now draws on what we've done in chapter 2, finding derivatives, and you have to be able to find a derivative and then do some algebra with it of setting it equal to 0 or finding out when it's undefined in order to be able to do this stuff. All right, moving on to chapter 3.2. You have the notes packet I gave you on Friday. That's going to be your notes for the whole unit, but I don't think there's pictures in there, so you might have that out to refer to as we talk about Rolle's theorem and mean value theorem. So on Friday, I talked about how there's several theorems throughout calculus, and we saw the first one back in chapter 1 with intermediate value theorem, and then we saw another one on Friday with extreme value theorem, and then today we'll see 2 more. One of them is Rolle's theorem, and it's not super important, but it's there, so we should look at it. And then mean value theorem is important. It's just a more general version of Rolle's theorem. So Rolle's theorem says if you have a function that's continuous and it's differentiable on this interval, and also the function outputs at the beginning and the end are the same, then somewhere in that interval the derivative has to equal 0. So we have 3 conditions. Our function's got to be continuous, and he's got to be differentiable, so no sharp turns. It's all got to be a smooth curve. And beginning and end are the same. As long as those 3 things happen, guaranteed the derivative is going to equal 0 somewhere in there. So just to kind of highlight this, I have this little picture here. We are closed at the beginning and at the end, and the heights are the same. So that's kind of giving us this thing, and we're going to be continuous. And then I'm going to draw a curve so that it's differentiable. It just means it's a smooth curve, no sharp turns. And no matter how I draw this curve, if I have to connect this first point to the last point with a smooth curve, somewhere the curve is going to flatten out and give us a derivative of 0. So here, where does that happen? Tell me when to stop. All right, so that's 1 and stop. So you might have more than one C value where that happens. You're guaranteed one. You could have more than one. I could try again and say, like, what if I try again? And tell me when to stop. Stop. All right, so right there, the curve is flat, so the derivative is 0 there. All right, so the game is trying to, like, all right, set up the beginning and the end at the same height, draw a smooth curve connecting them, and see if you can break Rolle's theorem. And you'll discover you can't. No matter how you draw this, you're going to have a point where the derivative is 0. Now that's not quite smooth, so let's move that out. All right, so stop. All right, so I can try all day long as my curve is a smooth curve and continuous, and it begins and ends at the same height. There's gonna be a place where the derivative equals 0. So that's Rolle's theorem. And if you're bored in your next class or here, you can see if you can try to break Rolle's theorem, and good luck, you won't be able to. Any questions with Rolle's theorem? All right, and then we'll come back and do a couple examples of that. But before we do, mean value theorem is a more general version. Mean value theorem says, all right, let's just say f is continuous and differentiable, period. And let's not worry about this whole business about the beginning and the end being the same. So your function's continuous and it's differentiable. Great. Then, somewhere in the interval, the derivative is going to equal the slope of the curve over the whole interval. So this is a little bit more complicated because it's more general. Rolle's theorem is just like a really specific version of mean value theorem. So somewhere along the curve, the derivative is going to equal the average slope of the curve over the course of the interval. So if you look at the picture here, you've got a curve. It's a smooth curve, so it's always differentiable and it's continuous. If I just play connect the dots from the beginning to the end, this is a straight line. That green line is what I'll call the secant line. Somewhere along the curve, the derivative equals the slope of that secant line. That's what this is saying. So all these words can kind of hide what's going on, so I think the picture is a little bit helpful, and the formula is maybe a little bit helpful of saying the derivative equals the slope. So this thing is just fancy slope. Derivative equals slope for some value inside the interval. And basically you have a tangent line that's parallel to the secant line somewhere along. So again, you can kind of try to draw a picture of that. I'll draw another one over here. So here's the beginning, here's the end. I'll draw a curve. And then I'll draw the line connecting those 2 points. So the line connecting those 2 points is the secant line. And we want the derivative to be the same as the slope of that secant line. And guaranteed it's going to happen somewhere. It's going to happen where the tangent line is parallel to the secant line. So if I line up my straight edge with the secant line and then just move it until it's a tangent line to the curve. Whoops, it's too far over there. So I'm going to move this so that it's tangent to the curve. There it is. So right there, we've got a tangent line that's parallel to the secant line. So right here, f prime of c equals the slope of that line. That's what mean value theorem is saying. And no matter how you draw the curve, so long as it's a smooth curve, you're going to have a point where the tangent line is parallel to the secant line. Ryan.
How is that applicable?
That's applicable when we want to find a point where the slope equals the average rate of change. So when we talk about what's the average rate of change, is there a point where the derivative is the same as the average rate of change? This becomes more applicable in word problems, which we're not going to get to this year. Sorry. But that's how it can be. On the AP exam, pretty much every year, one part of one of the free response problems deals with this. And it's like, you have to use your mean value theorem in some way. Now, No, because I didn't remember. I'd have to look back at it. But just about every year, they have you do either the intermediate value theorem, or the mean value theorem, or the extreme value theorem, or more than one of those on one of the parts of one of the free response questions. Now, only one part and only one free response question. You can kind of take the loss on that if you have to. It's not a big deal. And still get a 5 on the AP test. But the AP people love this kind of question. It shows up every year. So you got to know your mean value theorem when you go to take the AP test in 357 days or so. So what we're going to do today and tomorrow is see, okay, well, like, how do we use these theorems? And mostly it's going to be check your conditions. Are the conditions met? Is the function continuous and differentiable on a closed interval? Yes. Okay, great. Then figure out what's the slope from the beginning to the end. Figure out the derivative. Set those things equal. Or in the case of Rolle's theorem, find the derivative, set it equal to 0, and solve. And see what values happen inside the interval. So that's what we're going to be doing with a few examples, and then that's going to be what you have for your homework for the most part. Ryan?
For Rolle's theorem, can there be a sharp line?
Nope. For both of these, it has to be a smooth curve, no sharp turns, because both of these, one of the conditions is that the function is differentiable. So continuous just means the curve is always touching itself from one point to the next. Differentiable means all smooth, no sharp turns. So this curve right here is continuous, but it's not differentiable right there because of the sharp turn. So that's not allowed in either of these things for these theorems to apply. Any other questions? All right, so let's look at an example of kind of illustrating Rolle's theorem. Example 1. So let's make the camera too far. So here's your function, f of x equals x squared minus 3x plus 2. Find the x-intercepts. So you all do part A right now. I'll finish writing this down. All right, so over here, part A, example 1. What are the x-intercepts? How'd you find those? Wait, 0 and 1? 2 and, okay. Thought I heard 0. All right, so how do you guys get 1 and 2? Okay, so you factor it, so you have x minus 1 and x minus 2, and you set that equal to 0. All right, so you got your x-intercepts. set the function equal to 0, that factors nicely. That's simple. Once you got that, we want to show that the derivative equals 0 somewhere in between the x-intercepts. So if we had a graph of this, we have an x-intercept at 1, we have an x-intercept at 2, not draw the scale. Somewhere in between here, the derivative has to equal 0. So somewhere in between here, the curve is going to be flat. So what's the derivative? What is it? 2x minus 3. What do we do with the derivative? Set it equal to 0. And then what do you get for x? 3 over 2. Is that in between the x-intercepts? Yeah. So that is between 1 and 2. So check, proved it. And if you plug 3 over 2 back into the function, we'd get some y value. Probably it's a little bit negative. And so you'd have a point like right there. And the curve, you know, it's a parabola. You know what those look like. Ta-da! So that's what that looks like. Right there between the x-intercepts, you've got your place with the derivative of 0. So that's when they say on the homework assignment, here's this function. Prove or verify or show that the derivative equals 0 somewhere in between the x-intercepts. You got to find the x-intercepts. And then get the derivative, set it equal to 0, and see, does that equal a value in between the x-intercepts? If it is, great, you proved it. Any questions with example 1? All right. Example 2, we're not looking at the x-intercepts. Now we're kind of looking at just this interval. So for Rolle's theorem to be applicable, you need the function to be continuous and differentiable, because that's a polynomial. Check. You also need the function to have the same output at the beginning and the end. So you should check f of -2 and see if that's the same as f of +2. And make sure that Rolle's theorem is applicable. So if you plug in -2, what do you get? What's -2 to the 4th? 16. What's -2 squared? Times 2 is 8, so -8. Over here, when you do +2, 2 to the 4th is 2 times 2 squared is -8. So we got 8 equals 8. Check. All right. So between that and f of x is differentiable and continuous, we can say Rolle's theorem applies. Then you get the derivative, set it equal to 0, and see if where is the function's derivative equal to 0 in the interval. Now you might find a value for c that's not in the interval. You just throw that away. We don't care about those c's. We only care about c's in the interval between -2 and 2. So go ahead and get your derivative. What is it? 4x cubed minus 4x. Then what do you do? Then what do you do? How are you going to solve this now? Factor. Take out a 4x. What's left behind? Can you factor some more? Yeah. What factor some more? X minus 1, x plus 1. Solve. What do you get? 0, -1, and 1. Are they all in the interval? Yeah, so they're all C values. They're all C. Because all in the interval -2 to 2. If any of them were more than 2 or less than -2, you would throw that out and not let it be called C. So you can probably start looking at your homework for tonight. It's not due till Wednesday, so tomorrow we'll do some examples using mean value theory, see what life looks like, and maybe pick and choose some problems like what you're going to see on the homework more explicitly. If you were absent on Friday, take tonight to get the weekend's homework.